Hello, and thank you for tuning into this screencast on linear approximations here in our honors calculus class. Yesterday we introduced the topic, and today we're going to look at a couple more examples and we'll get started on the homework. Now, in example 2 here on my screen, you'll notice that I've already taken the first step of the process, which is to go ahead and sketch out the curve. The curve we're given in this case is the sine function, which we should know what it looks like. It's obviously a wave function graphed out where it starts at the origin and goes up, down, and back up through that first cycle of that first period of 2 pi. Now, what we're focusing in on, our neighborhood here that we're looking at, we're trying to get an approximation at around pi over 3. And the reason we're going to do that is we want to be able to approximate the sine of 62. Pi over 3, if you didn't know, is 60 degrees. So this neighborhood right here at 60 degrees that we're looking at is a neighborhood where we already know the sine of 60 degrees from our 30, 60, 90 degree triangle, which we'll talk about in just a sec. But go ahead and as you're sketching down the curve, I want you to note what we're looking for here again. Our goal is to find that linear equation. We called it yesterday L of x. That's the equation of that red tangent line. Okay, what that takes again is the point of tangency, which will be in blue, and then the slope or the derivative, which we calculate now, having had lessons like that in our first semester of calculus. All right, so if you need to, you can pause the video and play a little catch up on putting this curve together, but I'm going to go ahead and jump on in here with the first requirement, which is our point of tangency. We want to know what is the sine of 60 degrees. So we want to be able to say, what is the y-coordinate when I plug in the x-coordinate of 60 degrees, or pi over 3 radians? To do that, watch this, I'm going to pull back just a little bit, and I've got some of our trig review information that I went ahead and put together down here at the bottom. What we're going to do is we're going to be making use of one of our special triangles here to come up with that answer for the sine of 60 degrees. You'll remember sine is opposite of hypotenuse, so from 60 degrees the opposite side is square root of 3, and the hypotenuse is 2, so the sine of 60 degrees is radical 3 over 2, and that's what we'll put in for our y-coordinate here in our point of tangency. We've got square root of 3 over 2. All right, now, when we consider the next step, it's the derivative that we're looking for, the derivative of the sine function. So, as we consider what's the derivative of sine, we're going to want to evaluate that derivative when x equals 60 degrees, or pi over 3 radians. Okay? Now, you guys remember the derivative formula for sine, don't you? What is it? Go ahead and write it down. What is the derivative of the sine of x? Well, we know that to be the cosine of x. And again, we're going to evaluate that when x equals 60 degrees. So we want to know what is the cosine of 60 degrees. Again, if you need to, you can go back to this visualization. But what did we say? In this case, the cosine of 60 degrees is going to be the adjacent over the hypotenuse, which will be 1 over 2. Okay? So evaluating that derivative right there is very easy. We can find that the cosine of 60 degrees is 1/2, and therefore that's the slope of that line. So we now have both. We've got our point and we've got our slope. So you'll remember from class yesterday that we said the way that we come up with our linear approximation is we simply say, okay, y equals mx plus b. We know x and y from the point of tangency. We now know m from our derivative. We can plug and chug and solve for the unknown y-intercept, which is b in this case. All right, so let's do this. Now, I'm going to go ahead and plug in, instead of having things in terms of degrees, I'm going to use radians. I usually am a degree man, and I like to do my trig work in terms of degrees, but to keep everything nice and neat here, we're going to use pi over 3 as our x-coordinate, pi over 3. You might want to make a note to that effect, by the way. Our m value is going to be 1/2. That's the derivative. The y value correspondingly was square root of 3 over 2. So we're now going to need to solve for b with just a little bit of some work here. Why don't I multiply everything by 6? I like the sound of that. So 6 over 2 is 3. So I got 3 square root of 3. And then that's going to be pi plus 6b, just getting rid of those fractions. And then let's see here, subtract pi, divide by 6 maybe. So subtract pi and divide by 6. And that's what my b value is going to be. So another way of phrasing that, by the way, if you feel more comfortable writing it, pi over 3, square root of 3 over 2 minus pi over 6 will be another way of phrasing that b value. I don't care which way you show it. Now what we've got is we've got our equation. We've got L of x, or y, equals 1/2 x plus that b value, 3 square root of 3 minus pi over 6. Okay, and we're going to take that linear approximation right there, and in order to approximate it for the sine of 62 degrees, okay, that's what we're going to let our x value be. But do you remember what I said? We have to, in order to make this work well, we have to let 62 be in terms of radians. Okay, so in trig, remember to convert something from degrees to radians, we multiply 62 by pi over 180. And we simplify out by canceling those two units of degrees. And then 62 looks like 31 pi over 90 should suffice. 31 pi over 90. I'm going to take that, and that's going to be my x value that I plug in there. So in looking for this linear approximation at 62 degrees, we're going to end up with, I really don't want to write 62 degrees. So I'm just going to say, let's skip out that part. We're just going to say our approximation is going to be 1/2 times 31 pi over 90 plus 3 radical 3 minus pi over 6. And that will be my approximation. That's pretty ugly, I know. We've talked in the first semester about the need to be comfortable with ugly answers. Okay, so hopefully that doesn't throw you for a loop too badly. Yesterday we discussed how you guys are going to have a little homework assignment on delta math, and in fact we looked at one of the first types, this level 1 linear approximation question. It was pretty straightforward. I'd like to wrap up this brief screencast by looking at this level 2 linear approximation question. Okay, so I just pulled this from my delta math assignment, and it's going to be very similarly phrased, but down at the bottom down here, we're going to be asked some specific questions. We want to make sure we know how to answer them. So let's break down this example. This will be your second example to take notes on for today. Okay. Now it says we've got this unknown function f of x, or rather in this case it's a known function, pardon me, negative 3x to the 1/5. Now it says what's the approximation at x equals negative 0.9. So the first step normally would be to graph this out. Okay. I'm not a super big fan of graphing radical functions like this, but this one is going to be, I'll go ahead and do my best to make an approximation for what this curve will look like. And we're round about the neighborhood right in here. Let's see if I can get a good, decent tangent line. Right around there at x equals negative 1. Okay, so your first step, just kind of throwing that together. Of course, you could use a graphing calculator to help you out to graph this function. Again, I'm just kind of shooting from the hip there. But what we're looking for, again, is point of tangency and the slope. We'll find the point of tangency by plugging it in, and we'll find the slope, of course, by taking the derivative. Plugging it in this case should be pretty easy. If x equals negative 1, then f of x, f of negative 1, is just going to be negative 1 to the 1/5 power. That's going to be the 5th root of negative 1, which is negative 1. Negative 1 times negative 3 is going to be a positive 3. So your point of tangency right up here, negative 1 comma 3, that's going to be plugging in for x and y, just like we've practiced. And then to find m, we want to find what f prime is. Okay, now this might be a good exercise for you guys to do in using your power rule. So remember, your power rule says pull the exponent out front, make it a coefficient, and then drop it by 1. Having already had a coefficient of negative 3 out there, we now have negative 3 times 1/5. And then it's going to be x to the negative 4/5 because we decrease the exponent by 1. And then we want to evaluate that at this neighborhood of negative 1. So negative 3, 1/5, negative 1 to the negative 4/5 power. Again, negative 1 to the negative 4/5 power is something that we should be able to simplify having had algebra. We know that negative 1 to the negative 4/5 power is going to be 1 over negative 1 to the positive 4/5 power. Raising something to the 4/5 power is like raising it to the fourth and then taking the fifth root of that. -1 to the fourth power is 1. The fifth root of 1 is 1. So this whole bit right here is just boiling down to 1. Again, your calculator can help you do that as needed. Suffice it to say, we're going to end up with, let me get this red bracket out of the way here. Suffice to say, we're going to end up with -3/5 is our slope. Okay, just working out the arithmetic there. So we got our point, we've got our slope. So what we can now do is we can now come up with the first thing that they've asked us for, which is that tangent line, right? I'll switch colors. We'll do this in orange, and we'll try and do it relatively quickly. Y equals mx plus b. Okay, the two negatives are going to cancel out. Subtracting 3/5. 3 is the same thing as 15/5. So that's going to be 12/5. Should be my b value. So y is going to equal -3/5 x plus 12/5. Okay. Now that matches up nicely, by the way, with my green line that I've kind of sketched out up here. It's got a negative slope, it's got a positive y-intercept, so I'm pretty happy with that graph. Now we want to use that to approximate what happens when f is -0.9. So in other words, I'm going to plug in, instead of x, -0.9, and then see what shakes out. Now -0.9 is -9/10. Let me see if I can do this without having to resort to using a calculator. The negatives cancel out. Looks like that's going to be what, 27/50, and that's going to be 120/50, getting a common denominator. So that's going to be 147/50. 147/50. Again, doing that approximation, we're just plugging and chugging. And then these drop-down menus, actually, I'm going to pull up the screen here. And can I type my answers in? I think we can. Let's see here, you guys, patient with me. -3/5 x. Whoops. Put x out there. And then plus 12/5. And then what was our answer for that second part? 147/50. And what you'll notice is what I want to show you is that it'll fill in down there at the bottom. Did you see how those 3 little question marks? When you type in your approximation, it's got the program is going to be to where it all automatically enters that value in. So now we can work on our little drop-down menus. So it says when x is less than 0 or greater than 0, the second derivative. So this is going to ask some questions on, and I do have to apologize in advance for not really having spelled that out in person. But remember, the second derivative just means that it's the derivative of the derivative. Okay. And the second derivative is a way for us to use a test of concavity. When the second derivative is positive, that's going to mean that that function is concave up. Please make a note to that effect. When the second derivative is negative, that's going to mean that that function is concave down. Okay, I don't think I've spelled that out for you guys in person yet, but what we're going to do is we're going to say, okay, well, what is x? X right here is -0.9. So when x is less than 0, all right, the second derivative is, and we just want to give the sign whether or not the second derivative is positive or the second derivative is negative. We can kind of reverse engineer this, to be honest with you, because if we look at the curve that we sketched out, that function right there is concave down. So I know the second derivative is going to be negative. And if the function's concave up, then the second derivative is going to be positive. But here we've got it being concave down, near the point of tangency, making that value. It's going to be a little bit of an over approximation. And actually, let me go back to my notes from, I believe, yesterday when I had a nice little picture. Yeah, there you go. See how when the function is concave down, that our tangent line overshot? In other words, it was above where it actually should be on the curve. Make a note to that effect, that when the function is concave down, your tangent line is going to be above the curve, and therefore your linear approximation is going to be too much. And if the curve was concave up, like let's say, I'll just kind of use this sine example. If we were down here dealing with a linear approximation, and we were trying to approximate right about here, then my tangent line would be below, and that's because the curvature is concave up. So when your curve is concave up, you're going to be under approximating it. When the curve is concave down, you're going to be over approximating it. So back here to this example, do you see how this tangent line is rather thick, but do you see how if we were to make just one little bitty tangent line right here, it is an over approximation right here at 0.9. Okay, what in actuality should be on that curve is below what we had on our tangent line. I know I should have said that in class. Again, I apologize for not pointing that out to you guys, but Delta Math wanted to ask about concavity. So in this case, our x value is negative. The second derivative is less than 0. The function's concave down, and so we had a little bit of an over approximation. And then you click our answer, making sure that we've got all that information typed in there. And then they do a great job of explaining that. They talk about all of the steps that we took, and then they go through and they run this what's called the second derivative test, and they talk about how to determine if it's an under approximation or an over approximation. All right, I hope that helps. You guys, this is due on Friday at 3 p.m., so bring me some questions to ask in person in class on Friday, and then hopefully you guys can have some good success using this method of linear approximation. So thanks very much for watching, and have yourself a great day.